Hello guys, I am Anderson Santos and this presentation I will be talking about my work in the study of computational modeling of yttrium and lutetium orthosilicates doped with trivalent high earth ions. Here I will present and comment some of results of this study where optimization calculations were carried out and to simulate intrinsic and extrinsic defects in the two matrices. So let's go. These materials, lutetium and yttrium silicates, are known and extensively studied due to their efficient scintillation properties and like a relatively high density, fast decay time, and excellent light output when doped with cerium. In addition, they also have other luminescent properties when doped with lanthanide ions. So, lutetium silicate has industrial application in the manufacturing of medical imaging equipment such as tomography equipment. And for yttrium silicate, in addition to its properties, appears as an option with low financial cost for the production of scintillators. Different types of structures are found for these materials in literature, and for this work we use a monocline material with spatial group 14, and the number of non-symmetric sites are 2 high-earth non-symmetric sites, 1 for silicon and 5 for oxygen for both structures. The aim of this work is to calculate the energies involved in the formation of different types of intrinsic and extrinsic defects, trying to help answer questions to improve the performance of these materials, whether in the process of synthesizing the materials to prevent or reduce defects in the material that may act as luminescence quenching centers in the case of intrinsic defect studies, as well as the properties of the material doped with high earth ions for the case of extrinsic defect. So, talking a little about the methodology used in this work, the approach in choice for this study was classical and static computational calculations, where ions interacting in the structures through interatomic potentials. For these calculations, we used the gulp code and the lattice parameters of the structures were obtained from the ICSD database. The interatomic potentials were based on the database available on the website of University College London, which were empirically modified to reproduce the matrix with a good agreement with the experimental data in the literature. Buckingham and Coulomb potentials were used to simulate the interactions of ions in the lattice. This potentials is commonly used to describe ionic and partial ionic solids. We use these kinds of potentials to describe interactions between high earth ions and oxygen ions. The first equations represent the interatomic potentials between two of such ions. Additionally, we added the three-body potentials to describe strictly the interactions between silicon and oxygen ions. And the electronic polarizability effect was included using the shell model of Dick and Overhouse. This approach consists in dividing the ion into two parts, whereby a core represents the nucleus and inner electrons of the ion, and a shell which simulates the valence electrons. And the multilateralism method was used to calculate the defects in the structures, which considers the solids divided into two spherical regions, where the region 1 is treated explicitly and the position of the ions is freely moved to achieve the low energy configurations, while in the region 2, the chemical species were treated using a quasi-continuum method. This methodology has already been successfully applied in several works for different materials. So let's start talking about the results of this study, saying that some of the results that will be shown here, we already been published these results in a paper last year. So now some results obtained in our calculations will be presented. So let's go. Now I will present the results of the calculations with the defects in the structures. So, now some results obtained in our calculations will be presented. First, it was necessary to obtain an optimized structure without defects with good agreement with the experimental structures. Some criteria have been defined to determine the quality of the optimized structure. The first was to compare the values obtained for the lattice parameters with the parameters of the experimental structure. In other studies with this methodology, it was determined that a good agreement in relation to the experimental lattice parameters is with a maximum difference of 5% for silicates and the precursor oxides. Some other criteria were adopted to evaluate the results obtained with the optimization of the structures, such as the structures of the higher oxygen and silicon oxygen polyhedra. That and other results can be found in our paper. Another important information is in all calculations in this work, we simulate the structures at 0 and 300 Kelvin of temperature. So these two tables show that the potential parameters were able to reproduce both structures with difference between experimental and simulated parameters below 3%. The difference of all lattice parameters for yttrium silicates are below 0.98% at both temperatures. That shows that the potential sets very successfully describe these materials. For the lutetium silicates structures, this agreement is less accurate, below 2.24% for room temperatures, but still within acceptable values. First, for intrinsic defects, which are the defects generated by a formation that break the symmetry of the structures involving vacancies or interstitial ions. This slide shows the types of defects calculated in the structures. These defects involve only vacancies and interstitial ions of one of the three types of ions that form the structure. In these calculations, the defects are far enough in the structures to not interact with each other, which are called unbound defects. The energy cost for all possible points individual defects, vacancy and interstitials were obtained, and energy to produce the unbounded intrinsic defects were estimated considering reactions of this table. The solution energy were normalized by number of point defects present in the final defects configurations according to the related reactions in this table. As an example, the solution energy obtained to Schottky defect was divided by 8, since this defect presents 8 individual point defects, 2 yttrium or lutetium vacancies, 1 silicon vacancies, and 5 oxygen vacancies. The interstitial defects positions considered for both structures are shown in this table. The interstitial positions were chosen considering the empty volumes in the unity cell for both structures and taking into account a minimum distance of 1.7 angstrom from the interstitial site to the first neighborhood species. So these graphs show the range of the energies per defect for each type of unbound intrinsic defects in deuterium silicate. Results shows that silicon Frankel pairs have a biggest defect energy, while oxygen Frankel pairs are the most favorable defect for both compounds in both temperatures. Same results was found for yttrium silicates. Well, the nature of intrinsic emissions in deuterium silicate and yttrium silicate, although not fully understood yet, can be partially explained considering that oxygen Frankel pairs are formed in the materials and the oxygen interstitials will sit in a position loosely connected to neighborhood silicon species, leaving the possibility for this ion to anchor the electron-hole pairs. So, the lowest solution energy for each type of defects calculated for each structure are presented in this table, as well as the number of different configurations that were calculated. It is interesting to note from this table that increasing the temperature from 0 to 300 Kelvin, particularly all the solution energy is decreasing, and for the oxygen Frankel defects in deuterium silicon, the reduction was around 24%. The oxygen Frankel defect, which was the lowest energy cost in both silicates, is formed by oxygen vacancies and interstitial oxygen. For this type of defects, in case these point defects, oxygen vacancies and interstitial oxygens interacting in the structure, which are called bond defects, most of the energies found are smaller than that obtained for the unbound condition, meaning that the close proximity of the interstitial to the vacancy reduces the total energetic cost due to the Coulomb interaction between the effectively charged defects. So we will now begin to show some results of calculations of extrinsic defects in these silicates. The table presents the mechanisms considered that involve doping rare earth silicates. For each mechanism, a solid-state reaction is devised and respective solution energy equations can be obtained. The solution energies in both structures were calculated based on these reactions. Here is the graph of the default solutions energies. We see clearly that the defects with the lowest energy cost are those involving the replacement of 3+ host rare earth ions with 3+ doping rare earth ions. For both cases, in deuterium silicates, in both temperature, and yttrium silicate for both temperature. We also see that the doping cerium 3+ ion always gives a lower solution energy than the other dopants. These ions produce less distortion in the lattice, which may be likened to its ionic radiance compared to the rare earth hosts and other dopants. And like we see in unbounded defects, the solution energy value decreases with increasing temperature. That for both structures. So, as a conclusion of what was shown in this presentation, we saw that a set of potentials parameters was found empirically to yttrium oxygen and deuterium oxygen in order to reproduce yttrium silicate and deuterium silicate structures. And results also shows that oxygen-Frankel pairs are the most favorable intrinsic defect for both structures at 0 and 300 Kelvin, while all silicate-related defects showed much higher energetic costs. These results can be used to support the interpretation of the intrinsic luminescence found in these materials that are supposed to be due to self-trapped excitons stabilized to oxygen ions not bonded to silicon species. And that was exactly what was found for both structures, where the oxygen interstitials stabilized by the oxygen vacancies counterpart in the oxygen Frank defects are disconnected from the silicon polyhedra. And for extrinsic defects, our calculation shows that the most energetically favorable defects when our matrices are doped with high-earth ion 3+, replacing the host high-earth ions. And the doping cerium 3+ ion obtains the lowest solution energy, which may be likened to the difference in its iconic radius in relation to the other high-earth dopants. And we expect more promising results from what we have in relation to extrinsic defects in these silicates. And so finally, I would like to thank the institutions that supported and support this work, our research colleagues, and thanks for watching so far, and I will be waiting for your questions. Thank you again.